All right, let's say we're interested in the kinetics of this particular reaction. We're going to look at the kinetics of 3 ions of copper 2 reacting with solid aluminum going to solid copper plus aluminum ions. What we see here is that in the solution phase, not in the solid phase of this reaction, but in the solution phase of this reaction, we have a copper 2 solution, which is blue, going to an aluminum solution, which is colorless. And so if we imagine looking at this solution over time, we recognize that the color of this solution would go from blue to colorless. And we could set up a system, like with absorption spectroscopy, we could set up a system where we would look at the blue color by seeing how much red or orange light is being absorbed over time. So we'd look at the absorbance of red or orange light with time. And we'd start with a high absorbance because a lot of the red or orange light would be absorbed at first because there's a lot of blue present. And then over time, it's going to drop. The absorbance is going to drop as the blue color disappears. Now, the way it drops could go a whole bunch of different ways. It might look something like this. It might be linear, or it might follow some pathway like this, where it kind of tails off. And what we learn is that by analyzing the way that the blue color disappears, which is, corresponds to the concentration of copper 2 ion, the way the change in the concentration of the copper 2 ion, the way that happens with time, gives us insight into the order of the reaction, of the rate equation, with respect to the copper 2 ion. So let's just say we know that the rate for this equation happens to be equal to K times the concentration of copper 2 raised to some power x. What I'm trying to say here is that analyzing this data, how the copper changes with time, will allow us to find the value of x. And we're going to show you how you do this for 3 different types of reactions, or I should say 3 different cases. And those 3 different cases are going to be the case where the reaction is 0th order in our copper concentration, where it's 1st order in our copper concentration, or where it's 2nd order in our copper concentration. So here's what we'd see experimentally in each particular case. If we were looking at a process where the concentration of copper with time is 0th order, so we're going to look at the concentration of copper ion with time. If it's 0 order, that means it does not depend, the rate does not depend on the concentration of copper. So it's concentration of copper units of molarity. What we would see is a decrease in the copper ion concentration that did not change. It remained constant or linear throughout the entire process. If it's 1st order decay is what we'd say, 1st order loss in the concentration of copper, or 2nd order, the loss of copper ion, the loss of the concentration of copper ion, is going to kind of follow like a curved path. So that tells us that the rate is going to change depending on how much copper is present. And that rate of change could either be 1st or 2nd order. These are a little bit more difficult to differentiate. This one, it shows up right away. There are equations that describe this process of copper loss. Here are the equations for each of the various processes. In 0th order, what we'd see is the concentration of our copper with time is going to be equal to the original concentration of copper. That's this point right here. That's our original point at time 0. That's why we put a 0 here. Minus the rate constant for the reaction times time. That's this rate constant. Just a linear decay. For 1st order, the equation looks like this. The concentration of copper with time is going to be equal to the concentration of copper ion that you see originally, again, that's right here, times the number e to the negative kt. And then finally, in a 2nd order process, the equation is going to look like this. The concentration of copper at our various time points along the curve is going to be equal to the concentration of copper originally over 1 plus the rate constant times the time times the original concentration of copper. These are 3 different equations that will help us relate or figure out where should we expect the copper concentration to be as time plays out. Notice that in every case we can find this if we know the original copper concentration, we know the rate constant for the reaction, and we know the time where we're trying to find, let's say here, we know the time where we want to find the copper concentration. Once again, original copper concentration, of course we know the value of E, the rate constant, and the time. the original copper concentration, the rate constant, and the time. Now, what we often do is we linearize these equations. We linearize these equations so that we can take these data, we can plot them in a different way so that we can see, based on whether the line we get is, well, the curve I should say we get is linear or not, that is diagnostic of which of these processes is happening in our reaction of interest. So let me give you the linearized equations and then go over how this analysis works. So this equation already is linearized. So for example, if we let the concentration of copper be y, and we let the slope of a line be the rate constant, so k is m, we let time be x, and we let this be the y-intercept, we get an equation that looks like y equals mx plus b. I mean, it's negative mx plus b, but this just tells us our slope is negative. And so what we see is that if we simply plot the concentration of copper that we see in the reaction on the y-axis, which we've done here, versus time on the x-axis, again, which we've done here, if we see a linear result, then we know the reaction is zero order with respect to the thing that we're looking at. And more so because the slope of this line is k, the rate constant, we know that the slope of this line was the negative of the rate constant. All right? So that one's easy. The other one, you got to do a little bit of algebra to linearize this equation. And if you do that, you get an equation that looks like this. The natural log of the concentration of copper at time t is going to be equal to the natural log of our original copper concentration minus kT. Now, this is a little different, but what we do here is we say, okay, we're going to make the natural log of our copper concentration at time t, all these points here, we're going to take the natural log of those points. We're going to call that y. We're going to call this our intercept. And like we did before, we're always going to do this in all three cases. Our slope is going to be the rate constant, and our x-axis, our x value is going to be the time. And you can see here, we have now linearized this equation to make it in this particular form here. And then what we do is say, okay, we've linearized this equation. What we can do instead of plotting the data this way is we can say we are going to plot on the y-axis, here's the y, we're going to plot the natural log of all of these individual points, the y value for all these individual points, we're going to plot those on the y-axis. And we're going to plot that versus time. And according to this linearized equation, if we do that, and the process is first order, we should see a straight line with a negative slope. So if you take these data and you plot them not as the concentration of copper versus time, but rather the natural log of these concentrations versus time, and you get a straight line, you know that the reaction is first order with respect to copper concentration. And again, what's more, because we defined the slope of this line as k, the slope of this line is going to be the opposite of the rate constant for the reaction. So we can do this trick also with a second order process. And the equation, the linearized equation for a second order process looks like this. 1 over the concentration of A at time t is going to be 1 over the original, sorry, I'm putting A's in here, we do that in general. 1 over the copper concentration at time t equals 1 over the original copper concentration plus KT. I'm going to write this again because that's really messy. Forgive me for that. So 1 over the copper concentration at time t is 1 over the original copper concentration plus KT. So you can see this is linearized. If we make 1 over the copper concentration, we make that equal to y. We make 1 over the original copper concentration, this value here. 1 over the original copper concentration, we make that equal to the intercept. And once again, we make k equal to the slope and t equal to x. And we've got our equation for a line. And in this case, hopefully you can see what we're going to do is we are going to plot to test for a second order process. We'll take all these y values, all these copper concentration values, whatever they happen to be. We're going to take 1 over those, 1 over the copper concentration at the various time intervals. And we'll plot those versus time. And if we do that, we get a straight line. In this case, a straight line will go up for a second order process. If we see this, this is diagnostic for the reaction being second order in the concentration of copper ion. And in this case, the slope of this line, the numerical value of the slope, will be equal to the rate constant. So if this were the case that we saw in zero order, we would say the rate of the reaction is equal to k times the copper concentration to the 0 power, because anything to the 0 power is 1. The rate in this case would be equal to k. In this case, we would say the rate is equal to k times the copper concentration to the first power, and we just wouldn't need to put the 1 in at all. And in this last case, we would write the rate is equal to k, our rate constant, times the concentration of copper to the second power. And in each of these cases, we'd be able to find the numerical value of the rate constant by looking at the slope of this line. In the next video, we'll do a problem that takes you through this with some data.